SAHNE, self-serving assets in a highly networked environment. A software architecture project by the Distributed Information and Automation Lab at the Institute for Manufacturing, University of Cambridge, UK, for the Boeing Corporation. Imagine if parts on an aircraft, like the life jackets, instruments or landing gear, could talk and had intelligence. What might they usefully say? If they had the ability to sense themselves and their immediate environment, they could assess their status and make individual and collective decisions about their future. If they could communicate over the web, they could organise and authorise their own repair or replacement, or even their refurbishment for reuse on another aircraft. Does this sound like science fiction? Well, this idea forms the basis for this very project. Since 2003, Boeing has been sponsoring research at Cambridge. Close relationships have been forged with particular departments and specialist research groups. At the Institute for Manufacturing, the Distributed Information and Automation Laboratory, known as DIAL, started working with Boeing when they were promoting a worldwide initiative to set standards for the use of radio frequency identification, RFID, in the aerospace sector. DIAL created the Aero ID research program, for which Boeing was a lead sponsor.
What's the role of DIAL in bridging the gap between academia and industry?
The IFM itself has a broad role in that area. It aims to be the sort of the meat in the sandwich between academic developments and industrial needs. And DIAL, the Distributed Information and Automation Lab, takes on the specific role looking at those bridging needs in the information and automation sectors.
So what does DIAL do?
Well, our activities range from really quite strategic developments, helping organisations to look at their needs for automation and information solutions by, for example, examining their responsiveness to changes in their operations or to the need to reconfigure in the face of change. And so we look at strategic issues aligned with that, and also develop technologies that help support the capability of an organisation to deal with changing conditions.
What are the range of the industrial applications?
Historically, we began as a manufacturing research group looking at manufacturing automation and information applications. But over the years, we've expanded to cover really the entire supply chain. So right through from design to production, distribution, support and service, and actually end-of-life retirement issues. Particularly over the last 5 years, we've had a large focus on the service associated with complex engineering products and their maintenance. Well, SAHNE actually was an ideal fit for a number of the objectives and the technologies we were developing here. A key objective we had was to understand better the ability to use distributed information and automation systems in a service and support environment, and SAHNE exactly fitted that. Secondly, we're interested to examine the role of technologies such as multi-agent technologies, radio frequency identification technologies, and so-called smart or intelligent object technologies. And this project was a perfect basis for that work.
The SAHNE project was born as the result of the Strategic Technology Development Partnership between Boeing and Cambridge, and our discussions on the potential advancement of supply chain visibility and utilization using automated identification technologies and multi-agent systems. The project was influenced by the plan to widely adopt RFID tagging of parts used on commercial airplanes. Cambridge researchers accomplished the challenging tasks of automating the identification of part replacement requirements and then automating the part procurement process itself. Throughout the project, as Cambridge achieved agreed functionality, Boeing added new stretch targets in order to push the technology development envelope. Cambridge successfully met all the challenges and achieved a set of scalability factors that are impressive. The results of this project form a foundation upon which our supply chain experts will build and will guide our development in supply chain automation for some time to come.
Originally, Boeing wanted to use microprocessors attached to aircraft parts that would know their own expiry date, communicate with each other, and come up with a collective reorder of replacements automatically. With applicability to all commercial aircraft, this was the gauntlet thrown down by Boeing. DIAL examined this idea and suggested an alternative which would reduce the hardware issues with part-to-part communication. Based on each part having a unique identity, they decided to allow the components to interact in a virtual world. Each component would be represented by a software agent, which would cooperate autonomously in this community. Other software agents would represent communities of identical components, for example, everything from instruments to life jackets. This is how it works. SAHNE holds data on parts of an aircraft in a configuration database. It also has information on the condition of the parts held in another database. A third database contains the maintenance and overhaul schedules for all parts. Each component, such as a life jacket, is uniquely identified and has its own intelligent software agent. For each type of component, there is a software agent that looks after that community of components, called the Community Manager. The individual components check the condition database periodically to see if they need repair or replacement. If they do, they communicate this need to the Community Manager. The Community Manager checks with the other components of the same type to see if any are close to needing replacement or repair so that a batch order can be generated. Other life jackets check with the condition database. If they have a near-term replacement need, and if the answer is yes, they signal this to the Community Manager. They are then able to join the order, increasing the batch size and thus reducing costs. A new software agent now comes into play. This agent, known as the Yellow Page Agent, acts as the link to find potential suppliers for the Community Manager. For instance, I'm looking for life jacket suppliers. I will find suitable suppliers for you. Here is my request for a proposal. Suppliers, also represented by their own agents, then respond to this request. The Community Manager issues a preliminary contract, and the supplier agent is free to accept or reject the contract. Should more than one supplier respond, or should there be requests for the same thing from more than one Community Manager, a competition alert is raised. This brings into play an auction agent that can run a number of different types of auction depending on the situation. Finally, a contract and price is agreed, and a new life jacket is sourced. The Community Manager acknowledges the arrival of the new part and creates a new agent for the new life jacket and updates the relevant databases. It seems obvious that these ideas could be extended to cover all rotable parts. The implications for parts management and fleet configuration control are obvious. So now we have shown you how SAHNE works, let's look at the real thing. For the SAHNE platform to run, it first has to be configured. This is done in 3 stages. The first sets up the computing architecture in which SAHNE operates. It can be run over one or more server nodes, and details of these have to be provided. The second stage is to specify the aircraft parts that SAHNE will be sourcing. Here we say how many aircraft we will work with, what component types each aircraft has, how many are fitted to each aircraft, and for each type, what is their lifetime before replacement. Finally, we need to specify the parts source base. For each source, we provide their name, company ID, details on their size, whether they are a warehouse or manufacturer, their Yellow Page contact details, location and associated transport costs. Also, we list the component types the supplier can provide, current stock levels and unit cost. Some components can be refurbished, and this is also shown here. Once all these details have been completed, the configuration file for SAHNE can be generated and SAHNE put into operation. As SAHNE runs and orders are automatically generated, their status is displayed. Here we can see the electronic product code, or EPC, of the part that caused the order to be raised, its type, status, why it was ordered, who is supplying the replacement, and the date of the request. Orders and their progress can be tracked also. Here we show a list of live orders, and by selecting one, in this case for fire extinguishers, the details of the interactions between the various agents can be displayed. The SAHNE platform has been demonstrated with in excess of 4,500 component agents, making calls on suppliers at any one time. These scalability tests demonstrate the robustness of the platform, and while increasing the numbers of parts looking for replacement increases the time to resolve orders, at the highest density of demand, orders were automatically placed within 7 minutes. Dial have been exploring further opportunities to apply this research work with Boeing. We have new ideas on how the concepts and processes developed in SAHNE could be extended across the company. We are also exploring how our skills might be exploited on future research projects.
Well, I think SAHNE is very exciting because if you look in the academic or industrial literature to date, there are very few industrial strength deployments of technologies such as intelligent agents. And this was an opportunity for us to get involved in a project that from the very outset had its intent to deploy and disseminate these sort of technologies within a very large industrial organisation. That was really a unique opportunity.